So the techniques that we've looked at so far all involve that cross-sectional face basically being a circle, or when we turned it into a cylinder, it became a rectangle, but it still involves circles. And of course, not everything has circular cross-sections. Right? We're going to find the volume of this rectangular pyramid. Now, there it is, base AB, height H. So it's a shape we know the volume of already, so we can show that this does work. Now, I could take a cross-section and get a regular shape all the way through. That's what I want. Now, if I was to take a vertical slice, I would get trapeziums, wouldn't I, as I would move along. We get different shaped trapeziums. If I was to go horizontally, then I'd get rectangles. I think that's probably going to be the easier way of doing it. So if I slice in, thickness, well, I'm going to introduce a pronumeral Z there. Let's say the width is X and the height is Y, and I want X and Y in terms of the height. Z's representing the height of the pyramid. So there's our shape. The thickness, as I say, is in terms of Z. So the area is XY, but I want it in terms of Z. That's not in terms of Z. How on earth do I get it in terms of Z? I need to come up with some formula. So let's have a look at it. Let's just have a look, first of all, the X value. So that was the one I called the width, wasn't it? So if I was just to look there at the shape, what I'd end up with is a triangle. So I'll bring it back to 2 dimensions. So I'd see a triangle. Its base would be length B, and its height would be H. And we've just taken a slice, which we said the thickness was Z, and we're calling the slice thickness X at any particular excuse me, point. So how can I come up with a relationship of Z, how high it is in terms of X? Well, there's a couple of ways I could do it. I could use similar triangles. So I could say I've got the large right angle triangle here, the height H, base half B. Or there's my second right angle triangle at the top there. The height of that would be H minus whatever the Z value is. And the base would be half of X. And so using the ratio of sides in similar triangles, I could then say, well, H over half B would be the same as H minus Z over half X. And from this, we should now be able to play around with it and come up with a formula for X in terms of Z, remembering H is a constant height, B is a constant width. So the only pronumerals in there, or variables, probably a better word to say, only variables in there are Z and X. So let's rearrange it. Obviously, I can multiply to get rid of the halves in the denominator, cross multiply and turn it upside down. We end up with X equals B, H minus Z all over H. So I've now got an expression for X in terms of Z. Now, the other way I could do it is coordinate geometry. Even though there's no number plane there, I can still do it. Because I know it's going to be a linear relationship. What I'm basically going to do is say, what is the equation of this line? Okay, I mean, there's no axes there, but I don't need to draw an axis. I'm just going to say at any point, I'm going to have a Z value and an X value. And notice I placed the X value second because I want to end up with X equals, and we normally have the second pronumeral as equals in a formula. So I'm going to put the Z first and the X second. Now, Z represents how high it is. X represents how wide it is. So up at the top here, I must have coordinates H0. I mean, it's not actually a number plane, so don't worry about the position of the points. I'm just talking about the relationship between the height and the width. So at the top, the relationship is when it's H high, the width is 0. It's at its point. Down at the base, it'll be when it's at height 0, the width is B. So I now have these two coordinates that link the X and the Z together. Well, if I've got two coordinates, and I know it's a linear relationship because it's a straight line, I should be able to find an equation between those two using simple coordinate geometry. So the slope, you've got to be very careful. Make sure it's the second one. Don't get confused with the X and out of habit put it on the bottom. The second one, so B minus 0 over 0 minus H gives me a slope of that line of minus b on h. And then I can use my point slope formula. So I've got x minus 0 is equal to slope z minus h. And so we get, you can see, the same expression for x. I personally prefer the coordinate geometry way of doing it, but surprising how many people like the similar triangles. I guess it's just a personal preference of which you find easier. All right, there's the x one. Well, I'm not going to redo the whole thing for y, because the only difference was it was still the same pyramid, but it was a width of a instead of a width of b. So everywhere I see a b, I'm going to replace it with an a. And instead of the pronumeral being x, the pronumeral was y. So logically, I should have ended up with y equals a h minus z over h for the y value. So it saves me redoing the whole thing. Okay, so area we said was x times y. I've now got it in terms of z. Let's tidy this up a bit. So I've got ab over h squared times h minus z all squared. So there's the area of the cross-sectional face. So my volume elements, multiply that by delta z. Now, the limit as z approaches 0, z, remember, represented the height. So we're going from a height of 0 to a height of h. So we're going from 0 to h. And let's integrate. Remember, a is a constant, b is a constant. H squared on the bottom there is also a constant. So that can all come out the front. And all we're actually integrating there is h minus z all squared. So I can just add 1 to the power over the power, but remember to multiply by the coefficient of z, which in this case is negative 1 on the bottom there. Sub in the h, sub in the 0, and we come up with ABH on 3, which is what we recognise to be the formula for a rectangular pyramid. Remember, it's 1/3 of the prism. The prism would be length times breadth times height, 1/3 of that. So there's our formula. So whilst I used coordinate geometry in the method I did, I didn't actually have it on an x and y axes. I just said, okay, I want to get values that link the x and the z together. Let's try another one here. These ones are a little bit different in that they give us an actual formula for the base of the shape. And so it's like we're sitting a shape actually on the number plane. So this time it's got a circular base, x squared plus y squared is equal to 4, so a circle. But each cross-section is going to be a square. So let's try and attempt to draw this up. So the number plane in this case, imagine it lying flat. And so the base is a circle, radius 2. And every cross-section is going to be square perpendicular to the base. So I could put one in there. And then there'd be another one there. And there'd in fact be an infinite number. I've left a gap between so we can see what's happening, but obviously they'd be right up against each other. And the next one would go there, and there, and then there, and there. And slowly we get our shape filling in. There's another one. I tried to join up all those edges, a bit dodgy there. We get, I guess, if you can imagine it, a cylinder which has been shaved. Like a bit like a bike helmet, I suppose. Yeah, think about it. Anyway, we're going to find the volume of this unusual shape. Okay, so each cross-section is a square. The thickness is delta x, so we want everything in terms of x. We know the base of it would be twice the y value. So it's going to be 4y squared. Oh, because the height, it's a square, so no, the height's also then going to be 2y. So the whole area is 4y squared. And y squared, if I rearrange my formula, is 4 minus x squared. So all right, delta v then, 4 minus x squared times delta x. We're going to be summing up these. So it's the x values. We're going from minus 2 through to positive 2 of this shape. But it is a symmetric shape. So I'm going to go twice from 0 to 2. And also brought the 4 out the front of the integral. So twice 4 is 8. And a very simple integral to do, just 4 minus x squared. And we get 4x minus a third x cubed, 120 over 3 units cubed. So when they actually give us a formula for the base, I think those ones tend to be a bit easier, where they say, okay, the base is this, and then the shape on top will be, in this case I said square. Sometimes they might say an equilateral triangle, and so on, and you can work out an actual formula. Here's the one that they gave, been moved over a bit, in the HSC a couple of years ago. I think on your notes, the words aren't over the top there. I don't know what's happened there. But you can see it's this little wedge shape in the middle that we want to find the volume of. So imagine we've got a cylinder, and it's a quarter of the cylinder. And then inside that cylinder, we're going to chop out this wedge. We want to find the volume of that wedge. It was a very tricky question, so I thought it'd be a good one to have a look at. So they've given us all the necessary dimensions. The base here is an isosceles triangle, AB equaling AC. The length of BC is a constant A at the edge here. Midpoint of BC is X. Cross sections to AX are rectangles. So it's the slice. There's the cross-sectional face. It's a rectangle we're going to have to try and find the area of. And the thickness is in terms of, well, whatever pronumeral. We've got R for radius here. So let's attempt this. There's the rectangle. I'm, again, just going to call the thickness in terms of Z. I'll just introduce another pronumeral. So delta Z. The base, I'm going to say, is the X value. So there's, well, I've labelled it at the top there, but obviously the base is the same as the top. The height, I'll call Y, but I need to get formulas for X and Y in terms of Z. So again, let's look at these shapes. So yes, the area will be X times Y. Okay, I'm going to find Y first of all in terms of Z. Now, if I look at the direction I've called Y, and if I'm thinking of two dimensions, all I'm going to see is a quarter of a circle, that quadrant. The slice will be a vertical slice, delta Z. Okay. So I'm doing it using coordinate geometry. So I'm saying I want to find Y in terms of Z. So Z is going to be my first number in this relationship. Y is going to be my second number. But this is not going to be a linear relationship, because look at the curve. In fact, I'm expecting that to be, hopefully it'll turn out to be the formula for a circle, but let's see what we get. Up at the top here, Z is 0. I'm going to say I'm going from A to X in my slices, so I've defined 0 to be here. And R is the radius on top. By doing that, in effect, what I've done, I suppose, is made A the origin. And then I do know the equation for that quite simply, because I know that's our circle, x squared plus y squared equals the radius squared. Although it won't be x squared plus y squared in this case, it'll be z I'm using. So y in terms of z would be the formula for the semicircle. Y equals the square root of r squared minus z squared, and we'll be going from z values of 0 to r. Okay, there's y. I did y first because that was probably the quicker of the two. Now, in the other direction, we're getting, they said, isosceles triangles, wasn't it, the base? So there's our base, ABC. Our slice now would look horizontally there. There it is. It's the same delta Z. But this time I want X in terms of Z. Now, I can't change the Z values. I've now defined at the point A, Z will be 0 up to, at the point D, Z will be R. I can't change those for the second shape. So I've got to keep that in mind when I do this. So it looks like this time now I'm going to have a linear relationship because I've got a straight line there. Okay, so let's find coordinates. A, we said over here, I defined it to be, it's now the origin, so it's still going to be the origin over there. It's 0, 0. Coordinates for C. Okay, so at the point C, the Z value then is now R. Remember we said over here that our Z values were going from A to X, which was 0 to R. I didn't actually label X in there, but that midpoint, remember, was X on the original diagram. And the the X values are going from 0 to A. Okay, I should be able to get an equation of a line out of that. So my slope, the second coordinate minus the first coordinate, So it'll be A minus 0 over R minus 0. I get a slope of A on R. Put it in the point slope formula, and I'm going to use 0, 0 because obviously that's the easiest number to substitute in there. And I simply get x equals AZ over R. I've got an expression for x. I've got an expression for y. So now let's find our area in terms of z. So x, AZ on R, times y, square root of R squared minus Z squared. I've got a formula now for the area, totally in terms of Z as the only variable. So the element of my volume, let's multiply it by delta Z. I want to sum up all those slices, and again, we're going from a Z value of 0 to a Z value of R. So my integral, well, A is a constant, R is a constant, I can bring those out. Z I can't bring out. So I've got Z times the square root of R squared minus Z squared dz. All right, how are we going to integrate that one? Oh yeah, so to make it more obvious, I've multiplied it by minus 2, so there's my derivative of minus Z squared. To balance it out, then I've got times minus over 2 here. So I now know that is in the form of function x, or z in this case. It's to the power of a half. So add 1 to the power, 3 on 2, over the power 2/3. And notice I've swapped my limits around, but I've got rid of the negative sign. And you can always do that in integration. If you've got a negative and you don't like having negatives out the front, swap your limits around and it gets rid of the negative. All right, substituting 0, substituting R, and there we go, AR squared on 3. Now, it was a heck of a tricky question. Turned out the actual average for the state for that question was 1.01 out of 4. So it was quite a tricky little question. So the Cambridge one's the 6C, a few out of Patel. There's a couple of nice questions, I think, in 3C. I only picked a few out there, but they're nice. Have a look at it.